Everyone, today we are going to start with the basic design using an real-time operating system. How we have to design the real-time operating system we are going to see. First we'll see what is RTOS. Previous class we'll see in the definition. Today we'll see how the RTOS is going to be started. An embedded system with a single CPU can run only one process at an instance. See, in the embedded system, a CPU can run one process at an instance. Multiple processes are not going to be executed simultaneously, like in other systems. In the normal system, a dual core is there means multiple processes can be executed. Here, a single process at an instance will be executed. Process at any instance either may be an ISR, it may be a kernel function, or it may be a task. Any one can be executed at an instance. And it provides a running of a user thread in a kernel space so that their execution is going to become a very fast. It provides a effective handling of ISRs, device drivers, ISTs, tasks, or a thread. Handling these all the things are done very effectively. Disabling and enabling of the interrupts in a user mode critical section codes. Enabling of the interrupts, disabling of the interrupts for the critical section is going to be done in the RTOS. It provides the memory allocation, memory deallocation functions in a block and in a fixed block of memories. So it is not going to be working for the bits. Fixed block allocation technique it is going to use so it is going to be working for the allocation and deallocation of the memory for in a fixed block allocation strategy that it is going to use. It also provides for effectively scheduling and running and blocking of the tasks in case of number of many tasks are there. If multiple tasks are there at the time, blocking and running will be handled by scheduling algorithms. I/O management with the devices, files, mailbox, pipes, and socket. It is going to be using these things to handle this I/O management functions. It also provides a use of semaphores by the tasks or for the shared resources in a task or a OS functions. These are the facilities it is going to be providing for use of the shared resources. If you want to use the shared resources, you have to use the semaphores or some using the critical sections. You have to handle these resources, shared resources. Effective management of the multiple states of the CPU and internal and external physical or virtual devices. This it is going to be handling. This all the work is going to be done by the RTOS. Now we are going to see the what is hard real time and the soft real time. Hard real time is it is strictly adhered to the time deadline. It has to if any task has to be stopped means it has to stop within a specified time deadline. It cannot continue that way. It cannot miss the task. It has to stop there only. That is a hard real time. Take an example. Previous class also I have given the example. The anti-lock brake system ABS in a cars. Whenever the brake is going to be applied, it has to happen. If the brake that after pressing the brake, if it is misses, then accident may happen or skidding of the car may happen. Anything may happen. So the hard real times are strictly adhered to the time deadline. When an event occurs, it should be served within a predictable time at all the times in a given hard real-time system. The preemption period for the hard real-time task in a worst case should be very very small. In the worst case also the time should be very very small. The hard real-time RTOS is a one which has predictable performance with a no deadline miss. Even in case of sporadic tasks, sudden occurring of the events, at that time also it has to be working with the minimum time deadline. Automobile engine control system and anti-lock brakes are the examples of the hard real-time system. Here, disabling of the all other interrupts of a lower priority when running the hard real-time tasks. That should be taken care. Preemption of the higher priority task by a lower priority tasks. Some critical section codes in assembly to meet the real-time constraints very faster. The tasks which are running in the kernel space. This is because of tasks are running in the kernel space, it is going to be taking a less time and it is going to increase the performance of the system. These are the some of the things of the hard real-time system. It provides the provision of the asynchronous IOs, provision of a logs and or a spin log, prediction of interrupt latencies and context switching latencies of the tasks. Interrupt latency means the gap between the one interrupt to another interrupt. See, whenever interrupt occurs, it is going to call the interrupt service routine. That gap should be a less. That whatever the gap is there, that is called as the interrupt latency. That should be very less. Context switching latencies of the task. Context switching latencies means, see, if any one task is executing at that time, higher priority task comes, then the lower priority task is going to be preempted. Then that lower priority task information is going to be saved and the higher priority task is going to be executed. That gap is there. Switching from the lower priority task to the higher priority task is there. No, that gap is the context switching latency of the tasks. Predictability is achieved by writing all functions which execute always take the same predefined time interval in case of the varying rates of occurrences of the event. The response in all the time slots for the given events in the system. And always it will give the responses for all the events, thus providing a guaranteed task deadlines even in case of the sporadic or asporadic tasks. Sporadic task means the task executed on a sudden burst of the corresponding event at a high rates. A sudden occurrences of the task, that is a sporadic task. Aperiodic means the task having no definite period of a event occurrences. When that event is going to be occurring, that we will not be knowing. That is a aperiodic. Periodic means it will be predefined. The task will occur after that one. That is the thing. Example of the hard real-time system is a video transmission. Each picture frame and audio must be transferred at a fixed rate. That is an example of the soft real time. Next is a hard real time. Sorry. Now we'll move for the soft real time. Soft real time system is, it is going to be almost trying to meet the deadline. Some deadline misses are acceptable here. That is a soft real time system. Soft real time means that only the precedence and sequences for the task operations are defined. Interrupt latencies, context switching latencies are small, but there can be few deviations between the expected latencies of the task and observed time constraints, and few deadline misses are accepted in the soft real-time system. Here context switching latencies are small context switching latencies are accepted here in the soft real time. In the hard real time they are not acceptable. Observe Next, a preemption period for the soft real-time task in a worst-case latency may be about few milliseconds. Only few milliseconds that time is going to be accepted. In the mobile phone, digital cameras, orchestra playing the robot, these are some of the examples of the soft real times. See, in the mobile phone, if you click on the any applications, take an example of the application, the Amazon. If you're clicking on Amazon, it has to open within a 5 seconds or 2 seconds. If it is taking 5 minutes, then also it's okay, because that is a soft real time task. If it takes some more few milliseconds extra, then also it is acceptable. That are the soft real time tasks. Got to know that one. Next we'll move for the real time operating system based system design principles. Design principles we are going to be seeing next. Certain RTOS for serving the interrupts. There are two levels of the interrupts are there. Fast level ISRs and the slow level ISRs, that are also called as the ISTs, interrupt service threads. The priority are the first for the ISRs and then for the ISTs. Then for the tasks. First the ISRs will be executing, after that IST will execute, after that tasks will be executing. Certain RTOS have a three levels also. Design with the using interrupt service threads. Using the interrupt service threads, how it is going to be designed. See, we'll see this one. See here, design with the ISRs and the threads. How it is going to be done? ISRs post the messages for the ISTs, and then the IST will be start the execution. Whenever the ISTs will receive the messages, then they are going to be start doing the computations. If RTOS is providing for only one level, then use of the task as a interrupt service thread. See, only two levels are, one level is there means first ISRs will execute, then thread will be executing. Next, design with the ISRs. See, design with the ISRs and the tasks. In this one, first the ISRs will be executing, then the task will be start executing. The first preference will be given to the ISRs. ISRs means interrupt service routines. The ISR will be posting the messages, then that message will be sent to the OS by operating system will give those messages to the task. The task will take those messages and it is going to start executing the thing. RTOS provide the nesting of the ISRs. Nesting of the ISRs means first level ISRs and the second level ISRs. Second level ISRs means ISTs. These facilities also going to be provided in this RTOS. Next, design with the this over. The design with the using interrupt service threads. Design in the form of tasks for the better and predictable response time control. Next is this predictable time controls. Here, provide the control over the response time of the different tasks. Here it will be see the response time of the all the different tasks. The tasks are assigned a different priorities, and those tasks which the system needs to execute with a faster response are separated out. Which task has to be executed first, that the system will decide, and it is going to give the time. In that one only it is going to be executing. These all things are going to be done based on the scheduling algorithms. Next, response time control. Before that one, we'll see another one. Task can wait and take the messages. Here, task can wait and it can take the messages in the RTOS. Whenever the task is going to be executing, it needs some components, it needs some resources, then it will be in the waiting state. It will be waiting for the IPCs or the any messages. IPCs and the post the messages using the system calls. Tasks are designed in a infinite loops. Here the task will not be closed or it will not be stopped here. It will be in the circular infinite loop. And execution of the task is synchronized by using the IPCs. The task execution is synchronized using the IPCs. When the frequency, when the frequent interrupt occurs from same source, then the message can be first put in the buffer on each interrupt, and when the buffer is sufficiently filled, then the IPC message can be posted for ready buffer. This is because if the buffer is not used and the IPC messages are posted frequently by making the system calls through the OS message queue post function, there will be a frequent context switching and lot of time spent in that one. Because of that, whenever anyone comes, when a message comes, it will not give to the it will not give that one information. It will be waiting till the full of the buffer fulls. When buffer is going to become full, then
Ma'am,
it
your
is
voice
going
is
to
breaking,
post
ma'am.
those messages using the OS message queue post command. Whenever you want message, a frequent
Ma'am, your voice is
decided that the other method is that even the ISTs or customers are parameters for say frequent posting of the messages by the functions from the ISRMC output. Frequent posting next model design. System of multiple tasks are going to be encapsulated and adopt one from user global tables in critical sections. The mux that it will be provided for the data caching. The module and each module consists of for a better readable sign control. Here they are using linear line of system. I would using a button vertical line control. They are going for the
ma'am,
button
your
line
voice
of
is
task.
very poorly.
Design the form of a task for the calculation. Here, no variables are not used in the task required. The ISR code should be a re-entry function or shade of others from shades or dates such as buffer or global variables. IVCs are used to indicate messages between a limited number of tasks. Now, for queues, messages should be globally shareable. Each should be shared with a source and encapsulated from the rest. Design taking care of in system calls. Here, expected execution time depends on the specific process of the embedded system. The memory time to provide a relative magnitude of time taken for based on a preemptive scheduler, a new parameter is going to be defined. It defines a time taken for an action test that could be emphasizing related magnitude of execution for the base action in a specific RTOS. Means expected general on a specific process of embedded system. And the layers tells this is based on the P and the P. And the memory is also includes IPC long than instead of using I. Okay, next is a design with a limited number of tasks. Here you have to select only the appropriate number of tasks to increase the response time to the tasks, better control over the shared resources, and reduced memory requirements for the tasks. You have to limit the number of tasks and you have to select only the appropriate. How much tasks are necessary, only that much you have to take an example of the ATM machine. See, ATM machine, how many tasks are necessary? One is card reader, second one is uh, after card reading, contacting to the bank, validating the balance, next the withdrawal or a deposit, lastly displaying the messages based on your work. Only 5 or 6 tasks you have to take. If you are taking more number of tasks, then it is going to increase the complexity, and also it is not going to give the good performance. You cannot expect the performance execution time of the tasks that will happen. So you have to avoid the limit the number of tasks. And another one, the resources will be shared between the tasks. If number of tasks are more, then it is very complex to share the resources. Use the appropriate precedence assignment strategy and use the preemptions. Preemption in place of time slicing. Instead of time slicing, you have to use the preemption. A task of a higher priority preempts the lower priority task. The ISRs are having the highest priority, so it is going to be executed first. Next, you have to execute the ISTs and you have to execute the tasks. If while executing any task, if ISRs comes, then the task has to be stopped. It has to be stopped and its information will be saved. Then it has to move to the execution of the ISRs. After completion, it has to check the which is the next higher priority. Then it has to execute. This like this it has to go for the execution. Next is the avoid task deletion. You should avoid the task deletions. Create a task at a startup only and avoid task deletions. Later at a later time. After completion, don't delete that one. Deleting only get the advantage of getting a additional memory space. If you delete, the interlinking will be there, the message passing will be there, IPCs are going to be used here, and the resource sharing will be there. If you delete that one, then it is going to the number of tasks will be waiting for infinite time. So you have to avoid the task deletion to make a semaphore deletion safe. Use a CPU idle CPU time for internal functions. The CPU may not be running any tasks. All tasks may be waiting for preemptions. The CPU at that instance may associate the RTOS for the followings. Read the internal queue, manage the memory, search for a free block of memory. These things will be done when it is in an idle state. You should not give the CPU in idle. Whenever the CPU is idle, you have to do some extra works like this. Next, design with a memory allocation and deallocation by the tasks. Here, if the memory allocation and deallocation is done by the task, then the number of RTOS functions are going to be reduced. This reduces the interrupt latency period as the execution of these functions takes significant time by the RTOS. See, you have to do the allocation and deallocation of the memory using the task. It is going to reduce the interrupt latency period for the execution of these RTOS functions. You have to use the fixed size memory block allocation method. Then predictability of the time taken in the memory allocation will be there. Fixed size memory block allocation strategy, if you are using, that is going to be helpful for you to get a predictable time for the allocation and deallocation. Next, design with taking care of shared resources or data among the tasks. ISR coding should be as like a reentrant function or should take care of problems from the shared resources or data such as buffer or global variables. If possible, instead of disabling the interrupts, only the task switching flags changing should be used. Only that will be good instead of disabling. That technique you can use to control the latency period. Latency means the gap, the switching from one task to another task. Whatever the gap will be there, the time will be there, no time gap, that is the latency. That you have to reduce as much as possible. Next, design with a limited RTOS functions. See, based on the application, you have to decide which all the RTOS functions are necessary. Only that you have to include. It is not necessary to include all the RTOS functions. Scalable RTOS, hierarchical RTOS, many types of RTOS functions will be there. Based on the necessary, you have to use. Use an RTOS which provides for creation of scalable codes. Only the needed functions include in the executable files and those functions of a kernel. And the RTOS not needed that own executable files. It will not include the executable files. Use of RTOS which is hierarchical. The needed functions extended and interfaced with the functionalities configured with the specific processor and devices. That facility you have to take care. Encapsulation using the semaphores. Semaphore queue and the messages should not globally shared variables, and let each should one be shared between a set of tasks only and encapsulated from the rest. A semaphore encapsulates the data during a critical section or encapsulates a buffer from reading the task or writing into the buffer by multiple tasks concurrently. Encapsulation using queues. A queue can also be used to encapsulate the messages to a task at an instance from the multiple tasks. Assume that a display task is posted a menu for displaying on a touch screen in a PDA. PDA means personal that device assistance. That one. A multiple task can post the messages into the queue for display. When one task is posting the messages and these messages are displayed, another task should be blocked from posting the messages. This is the thing how we have to encapsulate. We can write a task which takes the input messages from other tasks and post these messages to the display task only after querying whether the queue is empty. See, one after the other. See, you should not post all the tasks at a time to the device, one after the other. For that, we have to use the queues that is going to encapsulate all the tasks in one by one. It is going to display like that. You are going to be using. Next is a saving of memory and power. You have to use the save the memory and the power. Those functions you have to use. Use a compressed data structure that provided with a decompression algorithm. Use the compressed data that is going to save the memory. Compressed data structure combines together takes a less memory in the system. If you compress the data, it will take a less memory. See, whenever you want to mail more data, then what you are going to do? You are going to zip and you are going to mail. That is the saving of the memory will be happening. Like that, the compression techniques will be there. You have to use that one. Compression, decompression techniques. Make the code compact and fit in a small memory areas without affecting the code performance, called a memory optimization. These techniques you have to use. Use a declaration as unsigned byte, especially within the for loops and the while loops. If you use the signed integer, it is going to be fixed some memory for that one. If you are using unsigned means whenever it is required, it will give that one. That is the thing. Next, avoid the use of library functions. If a simpler code is possible, you can write by your own. Don't go for the library function. It will create a more data. Configure the RTOS functions. You have to, for example, if the queue are not needed for the RTOS queue functions are not ported in the ROM image. See, queue is not necessary. You should not use that one. Simple possible things are there. You give that one. Use a configurable, scalable, hierarchical RTOS in the ROM image for only the needed functions at the kernel. Only needed functions you have to provide. Optimize the RAM used for the stack. You have to use the optimization of the RAM. This is going to be done by the three methods: reducing the number of tasks that interact with the OS, reducing the number of nested calls, and call at best one more function from the other. Optimize the number of tasks. These all are the things for optimizing the RAM memory. It is going to reduce the use of frequent function calls and nested calls, and thus reduces the time and RAM memory needed for the stacks. So you have to reduce the use of the RAM. Optimize the allocation of the stack. As much as possible, you should optimize the allocation of the stack. Use the assembly codes in case of the software design. You have to use the assembly codes because assembly codes are faster than the high level languages. So try to use those things. Calling a function causes a context switching on a memory stack, and on return context switching is going to be retrieved. This is going to consume a more time. If possible, try to avoid these situations. Use the inline modifiers for all frequently used small set of codes in the function, or the operator overloading functions if the ROM is available in the system. Use the inline functions and operator overloading. That is going to reduce the calling of the functions. When a variable is declared static, the processor accesses with a less number of instructions than from the stack. See, use a static variable if shared data problems are tackled, and use a static variable in case it is needed. It needs a saving of frequently on the stack. If you are using the static, it is needed to save that data frequently on the stack. So try to declare the things as a static. If it is a dynamic, it will be continuously changing. Combine two functions if possible. Try to combine the multiple functions. If you are combining the multiple function, no RPC is necessary. If feasible alternative to the switch statement with a table of pointers to the functions. Alternative to the switch statements you have to use. When using the C++, configure the compiler for not to permitting the multiple inherent templates, exceptional handling, new style casts, virtual base classes, namespaces. This you can use. When using a Java, use a J2ME and configure the device class. That when programming in Java, you have to do these configurations. Then it is going to reduces the memory and power consumption. Memory. Now we'll go for the power consumptions. Here, methods of saving the and optimizing the power needs. First one is the circuits when with a smaller overall geometry. The system generates a lesser heat in the system with a smaller overall geometry and thus can be packed into a smaller spaces. See, if it is small, then small heat is going to be generated. If it is big, big heat is going to be generated. So to reduce that one, we are going to pack all the thing in a small. That is necessary for the embedded systems. Reduce the circuit glitches. See, CMOS circuit. In a CMOS circuit, what will happen? Power dissipation only at the instance of change in input. See, power dissipation, if what it is going to be done? Power dissipation will be there at the instance of change in the input. Therefore, unnecessary glitches and frequent input changes increases the power dissipation. If more glitches are there, more frequent changes of the input is there, the more power dissipation will occur. So, try to avoid these things. The VLSI circuit design have a unique way of avoiding the power dissipation. A circuit design is made such that it eliminates all removable glitches, thereby eliminating any frequent input changes. See, VLSI circuit you have to select such that it is going to be reduce the circuit glitches. That